My engineering design process, which is a sum of all my parts and all the professional development that I've been fortunate enough to be involved with, involves students looking at a problem, or it's a problem that they point out themselves, and then they try to devise a solution. How did that data drive your decision? Sometimes we'll go through and we'll give a little background. It just kind of depends on what it is. It's impressed upon the students that their initial design needs to be their honest opinion about how they would remedy a situation. And I'm looking generally for a production of an artifact. And it could be a system that they'll develop or a specific tool that they'll use.
3, 2, 1.
In this case, we developed a rocket to hit a target. Please draw your individual design for today. So I had them draw what their rocket would look like, make sure to note details as far as all the variables from mass, the number of fins, the type of fins, the orientation, and then also write a little justification statement of why they chose what they did.
At this point, we're transitioning from the individual design to a group design.
After their individual design, it's always a collaborative effort.
We definitely need to keep Idaho fins if we're going to add mass to it.
I always try to make sure there's 3 or 4 people, because with 2 you generally don't get enough varied opinions. So 3 or 4 is kind of my sweet spot, with 4 being perfect. Make sure everybody gets a chance to speak about their design before we discuss it as a group.
First of all, we definitely need a long rocket.
And the PSI somewhere between 35 and 40.
I was going to say, what if we did a little higher angle? Because you know how...
First off, each student takes their turn to talk about their individual design. The expectation is if I'm going to set that time aside for the students to individually share, they need to have something that they can describe. So they need to have plenty of descriptors, they need to have a drawing, so especially when sometimes vocabulary is lacking in some kids. If they have a picture, then they can fully portray to their group what ideas they're going with.
And then we can just adjust
we should do
them.
the angle 40.
35 and 40. Yeah.
Then what happens is I give them time to come together, whether it's a process of debate.
It would add like 30 feet if we added mass to
But we're lowering our angle.
Or whether it's compromise.
What about the mass? The mass, I think we should put it around 2 or 4.
Yeah, I'm thinking 2.
They work together to come up with a common group design, of which then I sign off on, and then they can start construction of their design. All right, here we go.
3, 2, 1. So close.
During the test, we collect data, then we'll come back and analyze the data. If they need to make adaptations because maybe it's at a different point in the process or modifications, they note that, and they always provide reasoning for their choices.
Since we added the 0.5 grams of mass, it got closer.
It added a bit of inertia to the rocket, so that way it went a little bit farther than it would have at the same PSI and angle.
And then after that, it's a cyclical process. Individual design, group design, build, test, reflect. And then when I look at their packet, which they'll turn in at the end, it will include all these pieces so I can see how their thoughts and how their product has evolved over the course of the lesson. I like this strategy because the students see the practical application of everything I'm teaching. It makes them think, it keeps them involved. As a teacher, it allows me to see physically what they're thinking, and it allows me to read what they're thinking and justify why they made the changes that they did.